All right, so today we're going to look to see what happens when we go to altitude with our oxygen, because of course we need oxygen to live. But our bodies are pretty amazing in their ability to handle lower and lower partial pressures of oxygen. So let's just talk about the gases in the atmosphere as it is. So we know the atmosphere is comprises different gases. For example, there's N2 gas. And this is around, 78.08%. Oxygen is the one we're interested in, and this is around 20.95%. And then you actually have quite a bit of this argon, and that's like 0.93%. You do have some CO2, and it's about 0.04%. And all the other gases, there's not a lot. I mean, you're talking about, in this case, less than 0.1%. And so if you can total all this up, right, get a total here, we would have 100%. And now here we could put percent here and put, our pressure. And this would be, typically we look at, in this case, we'll look at torrs, or millimeters of mercury. And in order to do this, we'd want to follow Dalton's law, which is simply, we can write it right here. We have Dalton's law of partial pressures. And this is our P total is going to equal P1 plus P2 plus P3. And we add all these up together. And if we do that, add all these pressures up, we would get a total of 760 millimeters of mercury. And this is at sea level. And now we can figure out the partial pressure of each gas by basically using this formula as well. And if we do that for oxygen, for example, because that's again what we're most interested in, right, is we would take our P of O2 would be equal to the P, let's see here, our P total, and you want to times this by the fraction of O2. And if we were to do this, so we take the P total, so 760, and multiply it by 0.2095. If we did that, we would get around 159 millimeters of mercury. Okay, so what I want to do is I'll erase this, and I want to start here with this atmospheric concentration, and we want to see what's going to happen when we inhale oxygen gas, and what happens to that partial pressure. We're going to go through what's called the oxygen cascade, basically, because the pressure is going to decrease with every step. All right. So let's start with the beginning. Our PO2, and this is going to be the atmosphere. Okay. Our atmosphere. And in order to do that one, we would just follow this equation, which was, I'll just, for reference, PO2 is equal to the P total, the P total times the FO2, right? So that's 760 times 0.295. And when we do that, we get our 159 millimeters of mercury. And this is atmosphere. We can just put atmosphere. Now we need to inspire that gas. So what is it going to be in the trachea, basically? And this would be the pressure, the PiO2 that's going to be inspired. And in this case, we have to look at also part of Dalton's law. When we inhale gas, we have the dry gas, and it's going to be humidified, and so they have to consider the water vapor. So in order to figure out what the PiO2 is, I guess I can write it here, PiO2 is going to equal our total pressure, and it's going to be subtract from the water pressure, and then multiply that by the fraction of O2. I'll put H2O again. Multiply that by the fraction of O2. And what does that give you? So we know that the total was 760. Here, water pressure is 47 milliliters of mercury. And I want to explain that a little bit more, because I think it is kind of interesting, actually. So if you have, let's say you have right here, there's the container, and there's H2O in it, right? This is full of H2O. You're going to have water vapor that's coming out of this, because water can exist in a gas, a liquid, or if it's cold enough, a solid. But this all depends upon the pressure of the water vapor. And what happens is, if you have water, as you know, if you heat water up, then the water molecules start to move faster, and so it creates a vapor or a gas, and they start to come out, right? And then eventually you have a gas. But what we see, though, at this, like let's say at 37 degrees Celsius, our body temperature, then you have a specific equilibrium that happens where the water vapor above the water is going to reach an equilibrium with the water that's liquid. And this equilibrium is going to always exist, and it depends on the temperature. And that equilibrium pressure is 47 millimeters of mercury. So if you have, for example, a glass of water, and you were to put that into a vacuum chamber, and you were to start sucking out all of the air, everything that's in there, that pressure would decrease. And if it gets low enough, down to 47 and lower, your water would start to boil at room temperature, because it has to reach this equilibrium, and you're continually sucking away that water vapor. And so eventually, if you could go to say 46, the water vapor would come out until the pressure goes back to 47, and then it will stop boiling. But if you keep on sucking it out, the water will just keep on coming out until all the water is gone into the gas phase. And then, of course, you can have things like the triple point, where you have water that's both ice, solid, and it's a liquid, and it's a gas, depending upon the temperature and the pressure, right? So it's a pretty cool thing. But we have to consider the water vapor, and in the lungs, the water vapor is there, and so we have to subtract 47 away from the total pressure. And when we take 760 minus 47 and multiply it by the 20.95%, then we're going to get the actual inspired pressure of oxygen. And that ends up being about 149 millimeters of mercury. Now it'd be in the trachea. All right, now we're in the trachea, we're inspired, but there's something else that's going on, is you also have another gas that is higher than the atmospheric gas because of what you're producing. What is that? It's CO2. You have CO2 gas that you're constantly being produced, right? Because you are consuming oxygen gas, and you are exhaling CO2 gas. But it's not always a 1-to-1 ratio. We remember that we have this thing called the RQ value, right? Or the respiratory quotient, the RER, respiratory exchange ratio. And this is basically the VCO2 over the VO2. And if, for example, with carbohydrates, we remember that if you have like C6H12O6 and it takes 6 oxygen molecules and it's going to combust that and make 6 CO2 plus your H2O molecules. Well, there you do the math, right? So 6 divided by 6 equals 1. But if you do the exact same thing for fatty acids, you're going to get 0.7 because that math would be, we have 16 CO2 from like palmitic acid divided by 23 O2, and we get 0.7. Anyways, mixed diet, as you know, 0.8 or so is the RER. So actually, we're going to use the 0.8 as a conversion factor in order to figure out what the partial pressure of oxygen is going to be reduced to, and that's called this alveolar gas equation. So what we want to figure out is the PA with a capital PaO2. And what does that equal? So here we use the alveolar gas equation. That's going to be, you start with your PiO2 minus your PaCO2 divided by R. Okay, so we know what R is, right? We're going to use a 0.8 is what we're going to basically use here, 0.8. And so we put 0.8 right here. Your PaCO2, we typically, when we measure that, it's around 40 milliliters of mercury. So we'll put 40, okay? So 40 divided by 0.8 is 50. And then we remember here, so, okay, if we do this whole thing, is 50. And then here the PiO2, right here is 149. So 149 minus 50 is going to give you 99, or we'll say, let's do the squiggly lines here, about 100 millimeters of mercury. And this is the alveolar amount, okay? All right, now there's one more step, because here we're at the alveolus, but we've got to go to the arterial side of things. So we actually have one more. So we'll do the PA, this is a little a this time, PaO2. And this is going to equal, pretty much, this is going to look at things like the QV mismatch, so your respiration, your ventilation and perfusion mismatch, your cardiac output, because different places of the lungs, they may not be a 1-to-1, for example. And then you have the diffusion gradients. We have, QV mismatch. And you also have, maybe diffusion issues. All of these things slightly decrease the PaO2. So it's going to be, 5 to 10 lower. And typically we'll look at, say, about 95 millimeters of mercury. Okay. And that's arterial. All right. And now finally, we're going to get to, we're in the arterial blood. So finally, we can put this oxygen-rich blood through the circulatory system and allow our mitochondria to start extracting that oxygen as the blood goes through. And in order for that to happen, well, the mitochondria are constantly pulling that oxygen. And the mitochondria don't need a very high gradient. The mitochondria only need like a 1 to 3 millimeters of mercury gradient in order to extract that oxygen. And then whatever is left after oxygen extraction ends up being the venous partial pressure of O2. So this would be the PVO2. Okay. And what is this basically? How do we get there, right? Well, this is essentially the AVO2 difference. All right, and we got to figure out what is that difference going to be. So let's come back over here, and we're going to go into the Fick equation, which we have talked about in detail before. But we'll use the Fick equation basically to understand what's exactly happening at altitude. All right. So remember that we want to look at the VO2. So our VO2, put a dot there, is equal to our cardiac output, that's Q, multiplied by the AVO2 difference. And we can do some calculations with this, all right, to figure out what this AVO2 difference is. We know that at rest, all right, so at rest, our RMR, our resting metabolic rate, is going to equal about 250 milliliters per minute of oxygen. All right, that's what we need. Our basal metabolic needs is about, for like a 70 kilogram individual, the RMR on 250 milliliters per minute. And we can calculate this because we also know pretty much what, so here, this would be what the VO2 is. We can figure out what our Q is also, because the Q, as you know, is a function of your stroke volume and your heart rate. And your stroke volume, somebody who, not an athlete will use, but a typical example we could use is 70 beats per minute, and multiply that by a heart rate of, say, 70 beats per minute. Beats per minute. Oh, stroke volume, I meant to say, not beats per minute, obviously. Stroke volume would be milliliters per beat, right? Okay, and then you multiply those together and you get 4,900. And now, once you take, so about 5,000, we'll just add that to around 5,000. And now if we solve for the AVO2, because if we rearrange the equation and solve for the AVO2, we would end up getting this portion right here, the difference, okay, would be about 5 milliliters per deciliter, okay? And you can do the math here. So if this product here equals 5 liters, and then it's 500 milliliters per deciliter, so that's per 100 milliliters of blood. So 5 times 5, right, 5,000, and then 5 times 5 is 25, so 250, yeah, so 5 times 5 equals 250 milliliters per minute, okay? That's how we know what this is. We can also get it from this way as well. So there's two different ways we can do this. We can actually measure in the laboratory the gas analysis, and then we can calculate what this would be. Or we could actually measure what these values would be. And like at rest, this A here is around 20. The arterial side is around 20 milliliters per deciliter. And the venous side is around 15 milliliters per deciliter. And so that's going to give you meaning you extract 5 milliliters per deciliter. And so there's two ways I guess we can do that, but you end up getting about 5 milliliters per deciliter. Okay, now we can take our 5 milliliters per deciliter, or if we know we're extracting 5 milliliters per deciliter, and then we can say, all right, we have 15 milliliters per deciliter, and we can put that into an equation, and we can calculate what your partial pressure is actually going to be at the venous side. And that maps well on the Bohr effect, right? Where we have the hemoglobin shift, where what would by changes in pressure, how much oxygen is, how much the hemoglobin is saturated with oxygen. Well, at around this 15 milliliters per deciliter, you end up getting around 40 millimeters of mercury. Okay, and this is at rest. At rest for both, we can say sedentary. Well, it's just for sedentary and elite. That's all it is. That's all that it needs to be. All right, around 40. I do want to just add, because this is going to help us understand why being in good shape helps you also handle altitude better. Because this AVO2 difference can change quite a bit with somebody who is in really good shape, right? Like an elite athlete. And let's say that you're, in this case, for a sedentary individual, this difference right here, at max exercise, this 15 right here, okay, for sedentary individual, this could go down, this is the mixed venous concentration. It's going to go down to, say, 12 milliliters per deciliter. Okay, so this is max exercise for a sedentary. Now, if we look at the elite person, okay, so here we have max exercise for the elite. Well, this changes. This can be, down to, we can even say, we'll just say 8 milliliters per deciliter. Now, so this is a pretty big difference in what this ends up being, okay? So this means that for the, during exercise, your delta, in this case, ends up being around 8. But in this case, the delta, you're thinking, oh, that's not that much more, because you're at 12 milliliters per deciliter for the elite. But it is actually a lot, because it's a 4 milliliter per minute difference. And that's a big deal when you talk about the Q, because you're going to take this and multiply it by that difference. Okay, so let's say that you have a Q of 20. So for like a sedentary, not very healthy individual, if you take 20 and let's say this is 10, and you multiply that by 10, then you get 200 milliliters. But if you multiply this by the 20 by 12, well, okay, so you increase that still by quite a bit by that 2 milliliters. But if this was 40, all of a sudden, that becomes a much bigger difference, that 2 extra milliliters. And so you end up making, we could do the math, I invite you to do it, but you end up increasing the VO2 max by like well over 10 percentage points, basically, just because this extraction difference is so large. Now, we can take this over here and we can figure out what would the exercising be for the partial pressure. What would that look like? So for the sedentary person, but at max exercise, this is going to drop it down to, say, maybe 25 millimeters of mercury, max exercise. That's as much as they can extract. And with the elite athlete, where they're pretty much extracting all of the available oxygen in those specific muscles that are going through the capillaries, but then, like I said, it's mixed, so that's why you end up going to maybe 8 milliliters or so, because it's mixed with like the skin, blood, and everything else that's not extracting all the oxygen. But it's still going very low. When you look at that, you're down to a very low partial pressure of, say, around 15. millimeters of mercury. And this is with the elite individual. Okay, so your elite individual during max exercise can really allow that to drop significantly. And this is the reason why, again, that can happen is because, again, the Q, this is their stroke volume, this is how strong their heart is, but this AVO2 difference is basically what is their capillary density, how effective are their mitochondria, how many mitochondria they have, so mitochondrial density, capillary density, getting that, if the heart is pumping the blood through the organs, but you've got to have enough capillaries to get those all through the muscles, and then you have to have a well-functioning mitochondria and a lot of mitochondria in order to extract all of that oxygen, so you can get these major extraction differences. And this makes a big difference for improving the VO2 max, as we'll see. But we also can see a difference when you go to altitude. So let's go to the extremes, all right? What would happen? So all this here is what happens at sea level. And I'll just point out that the diffusion gradient is high, right? Between this 95 here down to 40 millimeters of mercury, there's plenty of that diffusion. Like I said, the mitochondria only needs 1 to 3 or even less milliliters of mercury of diffusion gradient in order to get that oxygen to the mitochondria. So this is plenty of diffusion, 55, nearly 60 milliliters of mercury of diffusion in order to drive the oxygen into the mitochondria. So it's no problem. And then this is also like at exercise, for example, like down to 25. Look, that diffusion is even greater, and that's why your mitochondria can support exercise very well, because it makes such a high diffusion, and you can drive that oxygen right into there. The question is your mitochondria able to use that oxygen that is available? Now, when we go to elevation, things start to change a little bit, and you can start to see some separation between like an elite level athlete with really well functioning mitochondria and a high cardiac output, and those who don't have that. And we can do that based upon basically using this Fick equation, doing the same thing. So what we can do is pretty much do all this same math here, but we're going to do it for elevation, okay? So we'll just go like this, and now let's do it at altitude. So our PO2, okay, at Everest. Now, at Everest, the total pressure is going to equal about 253 torrs, all right, or millimeters of mercury. So we can do the exact same math that we did over here. We would take our 253, I'm going to come down like this, okay? So we'll take our 253 and multiply that by our fraction of O2, so 0.2095. Okay, and so if we multiply this out, we'd get about 42.4 milliliters of mercury. And now we need to do our PiO2, right? It's our humidifier. So our PiO2, so same thing, 253 minus 47, and then multiply that by our FO2, and this would equal, actually this is 42.4 because the other one is 47. Okay, so here we have about 47 milliliters of mercury. Yeah, and then 42.4, so it decreased a little bit. Now let's go to our PaO2. PaO2, and how to do that? We take our PiO2, which is 42.4, and we subtract, if we put 40 here, 0.8 for the R, what are we going to, we're going to get Look at this. 40.8 is 50. That's going to give you a negative 7, right? Negative 7 millimeters of mercury. You would die. You would not be able to live because you have a negative partial pressure of oxygen. Yet we know that people can be on top of Mount Everest, and some people have hiked without even any oxygen. How is that possible to do that? Well, it's because how cool the body is. See, what happens is this is at normal sea level, the 40, but when you're at elevation, you are hyperventilating. And so your PaCO2 decreases dramatically because of that hyperventilation. And so this ends up becoming closer to around 10, all right? So as this becomes 10, now you go 10 divided by 0.8 minus 42.4, whatever. Anyways, you end up getting a partial pressure of around 30 millimeters of mercury, okay? So this is closer to actually what you can get if you're hyperventilating enough, and that's hard to do. There's some serious hyperventilation in order to get your PaCO2 to 10. But this way you can bring your partial pressure of oxygen at the alveolus to 30. And then we're going to have some of the same problems with the diffusion gradient. The PaO2, right? It's going to decrease a little bit more. And so we could do your PaO2. Again, same issue. And so now, I don't know, we're going to be like 27 or something millimeters of mercury. So I guess I could have circled that. But anyway, so around 27, 30 millimeters of mercury. Well, that's very low if you consider this right here. Look at this. At rest, normally our venous partial pressure is 40. And yet at Mount Everest, our arterial side is down to 30. So that means in order for us to extract that oxygen, we have to have what? A really good AVO2 difference. All right, so let's go back over here. Our PVO2, we have to have a really good AVO2 difference. And what could that be? Well, hopefully you're like an elite level athlete or something, and you can be 15 to 20 millimeters of mercury. All right. This way, if you have really good mitochondria, they can extract and really pull all that oxygen. Then you have a diffusion gradient, right? 30 down to 20 or so 10 to 15 millimeters of mercury diffusion gradient, so your mitochondria can actually use the oxygen, you can survive. And now if you are, like I said here, if you are max exercise for a sedentary person, we put like around 25 millimeters of mercury. That means you probably couldn't be at the top of Mount Everest for even a minute. That's like as much as holding your breath, basically, because your diffusion gradient, like 25 down 27, you're like 1 or 2 millimeters of mercury. It's not enough to sustain your oxidative phosphorylation in the mitochondria. You have to have a really good functioning mitochondria in order to extract enough of that oxygen so you can do that. Now, of course, you also have to consider what your Q is, because you could simply increase your cardiac output. If you increase your stroke volume and your heart rate, then cardiac output increases, and then you can get your VO2. I just wanted to point out that it's really neat that if you have high density mitochondria, you can extract that oxygen, you can use it more effectively. But if not, and you can only use so much of it or something, you really need to, you can simply just increase your stroke volume or your heart rate, and that's why at high elevations, your heart rate tends to increase as well, because you're trying to maintain your needed VO2. Because your extraction levels, it doesn't necessarily go down more than it needs to. That's why, like at rest, your elite level athlete or your sedentary person, your PVO2 is still somewhat similar, right? 40 milliliters of mercury. It's not like your elite level athlete is putting it down to 15 just to rest. This only happens during maximal exercise. You can just increase your cardiac output. Okay, now this also, it reinforces some other things that I think are important for us to consider when it comes to things like hyperoxia or oxygen therapy or oxygen supplementation and all the claims about the benefits of extra oxygen. Some of those make sense and some of them don't make sense. If we look at this scenario here, we can see that if you're at high elevation, that extra oxygen makes a big difference because look at your partial pressure gradients, right? Normally you're at like at 195 milliliters of mercury at your blood level versus over here, you're down to 42 and that's as low as your venous level. And so providing supplemental oxygen at altitude at very high altitude makes a lot of sense, but this is extremely high altitude. In fact, if we did the math on this, 47, right? So if we took, if the partial pressure of oxygen is 47, right, at Everest, then we could simply go 760, divide that by, we do 47 divided by 460, okay, divide that and put that into your percent, and you're going to get around 7% oxygen. So in other words, people can live at the top of Mount Everest whereas only an equivalent of about 7% oxygen. Whereas in the atmosphere, we have around 21% oxygen. That's a huge difference. So, and we know that at other elevations, the oxygen equivalency is around 14-15% oxygen. And again, it's because with one breath of air, we have plenty of oxygen to sustain all of our body. So this AVO2 difference, we can actually look at this with the arterial concentration more. So if we could go CaO2, so the content of arterial blood, what is that really equal to? Well, we want to look at your hemoglobin levels as well as the amount that's dissolved in your blood, right? So you can look at, this would be equal to 1.34 times SaO2. This is basically how much your hemoglobin is saturated by. So 1.34, actually, forgot the hemoglobin. 1.34, yeah, times your hemoglobin times your SaO2. All right, and now you're going to add that to the amount of oxygen that's dissolved in the blood. So we do 0.003, multiply that by your PaO2, and we can figure this out. So with the hemoglobin, you're typically around 15 milligram per deciliter. So about 15 here. You can do about 98% is what you normally are. Your SaO2 is, and for your arterial pressure, right? 195. We can just use 100 right here, and we add this. So this ends up being 0.3 milliliters per deciliter. And this over here, 1.34 times 15, 98% of that. So you're around 20 milliliters per deciliter. So this is the hemoglobin portion right here, okay? This is the hemoglobin portion. This is the dissolved portion that's in the blood. You add those together, I mean, this here ends up becoming pretty much insignificant, right? 0.20 milliliters per deciliter, which is about, this is the same as 200 milliliters per liter of blood. Versus here, right, you have, so this would be like pretty much just 3 milliliters per liter of blood. this is really insignificant, right? I mean, just normal walking around, you're going to need like a liter of oxygen per minute. This is 3 milliliters of oxygen, so there's hardly any oxygen that's dissolved in the blood. Most of that oxygen is carried by your hemoglobin. That's why hemoglobin is so important. That's why, your elite athletes, they increase the amount of hemoglobin and blood volume. And so, this, like, if you have normal 5 liters, then an athlete could have like 7 liters, right? So it's going to be that much more oxygen, hemoglobin, and carrying capacity in their entire blood, which they need during that max exercise, but not during sitting down, not during sedentary situations. So you have a couple important scenarios. People sometimes are thinking that oxygen itself is the key to mitochondrial function, but that's not accurate, and we can see this from this Fick equation here, that often people who are not trained, they already have plenty of oxygen that's available, but their mitochondria are not able to use it. So oxygen availability is not what the problem is, it's actually oxygen utilization. And this demonstrates exactly that. You have already lots of oxygen that's available. Your PVO2 is around 40 milliliters of mercury, and max exercise, it can be 25 for an unsedentary person. There's still a lot of oxygen available. It's not being used. They're not able to. They need to increase their cardiac output, for example. They can use more of that oxygen. They can get the oxygen circulating through their blood. Now, of course, if you were to inhale 100% oxygen 100% oxygen, then this would increase. Maybe it would increase to around 18 milliliters per liter. But again, how is that even comparable to the already 200 milliliters you're already providing? And let's not forget that you're already providing way more than you need. If we look again at this AVO2 difference, for example, you're at 20 milliliters per deciliter, and then you are when you're at rest, you're at 15 milliliters per deciliter. So you're only extracting 5 milliliters per deciliter. So there's still plenty. Even if a sedentary person can extract, 5, 10 milliliters per deciliter more than that. And so you're able to, if your mitochondria are able to, and you actually needed the extra oxygen, then you'd be able to do that. But you don't need that extra oxygen. Your mitochondria are just either not functioning very well if they're not able to use that oxygen. So you're starting to use a lot of anaerobic metabolism, and that's why you have maybe higher lactate levels because your mitochondria are not functioning. Giving extra oxygen itself isn't going to benefit you because you don't need it. You already have a lot. In fact, every breath that you take, right? If you inhale just your normal oxygen levels, you're inhaling your FiO2 is equal to around 21, right? 21%. And your FeO2, your fraction of expired oxygen, is going to be around 16%. And as you start to exercise, the 16% stays pretty much the same. It might go down a little bit and then it comes back up, especially during maximal exercise. Why? Because you just breathe more. You just have faster ventilation. And that faster ventilation is simply going to allow more of the oxygen to dissolve into your blood to meet your needs. But you're still exhaling out 16% oxygen, showing that there's still plenty of oxygen that you need, and providing a little bit more oxygen dissolved in the blood isn't going to benefit you at all. And that's why we can thrive really well at these higher altitudes where the partial pressure is equivalent to even as low as 7%, right, at Mount Everest. Of course, that's not sustainable for longevity. That would end up inducing severe hypoxia over time. But living in places where it's only 15% equivalent of the partial pressure, that actually has a protective effect. And it makes sense when you think about the mechanism of what's going on. Oxygen is an oxidizer, and our mitochondria are extracting that oxygen so that it can make do oxidative phosphorylation and make ATP, but also that protects our cells from oxidation. Otherwise, the oxygen will just dissolve in the cell membranes and different areas and start creating oxidation because there's all this oxygen that's available, but your mitochondria either don't need it or they're not functioning well enough to actually use it. So providing additional supplemental oxygen when you clearly don't need it is not going to provide you any benefit. And if anything, it could be potentially harmful. So it's important to consider the fact that you can actually be suffering from, or not suffering, but you could actually have hypoxemia. So hypoxemia is when you have basically an SpO2 of, I don't know, less than 90, saturation levels. If it's like less than 90, this is hypoxemia, but it's not necessarily going to cause hypoxia. That's at the tissue level where your tissues are starving for oxygen. They're not able to get that. And a good example of this is this mismatch diffusion right here. Your elite athletes during max exercise, their cardiac output is so high that they can actually push their blood through their lungs so quickly that they have this big mismatch, and they can have this hypoxemia. It can even be like around 80 or even less millimeters of mercury, and so that's going to impair their physical exercise performance because their hemoglobin is not fully saturated, but they're not getting hypoxia. They're not getting like tissue hypoxia. They're still fine. Now these athletes, they could actually benefit from hyperoxia, so supplemental oxygen, because then their hemoglobin could be fully saturated. So as long as your hemoglobin is saturated with oxygen, you're not going to benefit at all from additional oxygen. Unless there's other things that are going on, and that can look at like diagnostic criteria, but for the most part, especially like healthy people, if anything, that additional oxygen could be potentially harmful for you, not helpful. And so when you think about people using oxygen, like at the sidelines, inhalation of oxygen, trying to like help recover or something, that's not going to do anything beneficial for you because you already have plenty of oxygen. That doesn't help speed up recovery. If you look at people doing like oxygen-rich water, for example, that also wouldn't make any sense because you're providing in like a liter of oxygen, there's only like 10, 20 milliliters of oxygen gas, and a lot of that can't even get diffused through the intestines into the blood anyways. And plus, when it diffuses into the blood, it's actually just going into the venous system, which is already deoxygenated blood. It's going directly to the lungs to pick up oxygen anyways. So all of these things demonstrate that it's not going to be of any benefit for you. If anything, some of the higher fraction of inspired oxygen when you don't need it, if anything, can cause problems for you. The goal is actually to supply just enough oxygen to maintain your SpO2 at a healthy, normal level. You don't want to go higher than that, otherwise you start risking oxidation. There's a lot of studies showing that, and that's one of the potential benefits of living at slightly higher elevation, slightly higher at altitude. So hopefully this makes sense and how amazing the body is when it comes to maintaining our oxygen levels, even at very high altitude, even like when the equivalence is down to like 7%. It's really amazing that our bodies can do that. And if you are exercising and staying in good shape, you can have a high cardiac output to help maintain your VO2, as well as healthy mitochondria, so you can help with this oxygen extraction in this part. So hope this makes sense, and we'll continue on.